Well, it's time to get ready for the final exam. I want to go through some of these problems on here. Let's look at this one first, the general solution of a system of differential equations. I'm surely going to give you something like this on here, right? So suppose we have this one. Copy it over here, you can see it. Suppose I have dy1 dt equals 2y1 minus 3y2, and dy2 dt equals minus 4y1 plus 1y2. Suppose I want a solution to this system. I now begin by rewriting it in matrix form. I write ddt to the left side, y1, y2 equals, and I can write this in matrix form. There's no functions of t, so it's actually just alone. So there's just a matrix 2 minus 3 minus 4, 1 multiplying y1 and y2, right? Remember how matrix multiply works. You take this times this plus this times this, and sure enough you get 2y1 minus 3y2. That's the right side here. This times this and this times this gives you minus 4y1 plus y2. So this product here is the right-hand side vector, 2y1 minus 3y2 minus 4y1 plus y2, right? This two-element vector. So this matrix equation here, this being the product, is completely equivalent to this system, right? Because these two vectors are equal if and only if this component equals this one and this component equals this one. So I can rewrite my system in matrix form like this. Now in general, if there's also a function of t here, then I have to add a function of t here. But I gave you the easier case where we have what's called a homogeneous system. No functions of t alone added on. So this is a homogeneous system of two linear equations in two unknowns, y1 and y2. How can we solve it? Remember, for the homogeneous systems, we can just find eigenvalues and eigenvectors of this matrix when it has constant coefficients like that, and constant entries like that. And so we need the eigenvectors and eigenvalues. Well, we try to find the eigenvalues. They're the solution of determinant A minus lambda times the identity equals 0, which means we subtract lambda from each diagonal element, obtaining this matrix. And the bars on the side mean determinant of the matrix, right? If you have a matrix, it's just a rectangular array of numbers like this. But if you put straight bars on the side, that's another notation for determinant. It means the number that you get by taking this times this minus this times this. So we multiply this out, we get 2 minus lambda times 1 minus lambda minus negative 4 times negative 3. And the eigenvalues are this determinant equals 0. Right? So what do we have? We have 0 equals, let's see, lambda squared when we multiply this out by FOIL, right? Minus 2 lambda minus lambda is minus 3 lambda. Plus 2 minus 12 is minus 10. So we call this the characteristic equation for finding the eigenvalues. Is now lambda squared minus 3 lambda minus 10 equals 0. This characteristic polynomial can be factored. Lambda minus 5 times lambda plus 2. Right? So to find the eigenvalues for this system, we just use the zero product property and say since the product is 0, either this is 0 or this is 0, so one solution is lambda equals 5, and the other solution is lambda equals negative 2, and those are the eigenvalues. All right, so there's the eigenvalues of the matrix of this homogeneous linear system of two differential equations and two unknowns with constant coefficients. How's that for a mouthful? Now you know why we abbreviate so much in this class. All right, there's the eigenvalues. Now how do we find the eigenvectors? There's an equation for those, right? Step 2 is to find the eigenvectors. The eigenvectors are found by solving A minus lambda times the identity eigenvector. You can use U or V or X, I don't care what letter you use, equals 0 for each eigenvector. So we do one for the first eigenvalue, 5, and one for the second eigenvalue, -2. When these eigenvalues are distinct, there's a distinct vector for each. And so we'll have this. What's A minus lambda 1? Lambda 1 was 5, so it's A minus 5i times U1 equals 0. We'll take 5 off each diagonal element times U1, which has two components. Right, this is unlike the eigenvalue equation, this is a vector equation. We have matrix minus a number times a matrix times a vector equals a vector. So it looks like this. This is a vector equation, a matrix vector equation. Now this says that, let's see, -3, -3, -4, -4 times U1, U2 equals 0. And we can write it in this convenient augmented form so we don't have to write it all out, right? This means this matrix times this vector equals this vector, this short notation. And what should happen always is the second row should be a multiple of the first one, so that you can add a multiple of this row to this one, and this one is inconsequential, right? It just says the same thing the first one does. It has the same solution set as the first one. So this boils down to the equivalent equation, -3 times the first component of U1, -3 times the second component of U1 equals 0. And this is equivalent to the eigenvector equation. An eigenvector is any vector that's not the 0 vector with all components 0 that satisfies this equation. So how can we find it? Well, let's rewrite it simpler. Divide through by -3 and write U1 plus U2 equals 0. Any vector that satisfies that is an eigenvector for this eigenvalue, except the 0 vector. So an easy thing to do is just look at these coefficients, and let's choose U1 to be the vector with this component first and minus this component second. And that will work, right? Because 1 times 1 plus 1 times minus 1 is equal to 0. You can always do that for these 2 by 2 cases. Choose the second coefficient first and minus the first coefficient second, or minus this one plus this one, it doesn't matter. And you can take any multiple of this, any non-zero multiple is, again, an eigenvector. So here's an eigenvector corresponding to lambda 1. Now we need to find an eigenvector corresponding to lambda 2. Sorry I have to do this over and over on the same board. I can't move the camera so easily. So let's try for the second one now. We want A minus lambda 2 times the identity U2 equals 0. And again, this is a matrix vector equation. Here's a matrix and a number, scalar we call it in this context, a number, times a vector equals a vector. Well, when we subtract lambda 2, which is -2, that's the same as adding 2 times the identity to this. So we'll add 2 to each diagonal element. 4 minus 3 minus 4, 3. That's A minus a -2 times the identity times the vector U2. It has 2 components. And all this has to add up to 0. So we write that in augmented form, 4 minus 3 minus 4, 3. You don't have to. 0, 0. You observe, again, the second row is just a multiple of the first one, so it falls out. If you did your computations correctly for eigenvectors, the second row should always fall out. And now this is equivalent to saying 4u1 minus 3u2 equals 0, which means we could choose eigenvector u2 to be the vector with this component first, and minus this one second, or let's take minus this one first and this one second. So 3, 4 is an eigenvector corresponding to this eigenvalue. Now, what our theory tells us, and you can try by plugging in and see why it works without doing the long proof of this thing. Then you say, oh yeah, I can see how to prove it. Is typically the way it happens. Two solutions, independent solutions to the system of equations are eigenvector 1 minus 1 times e to its eigenvalue t, 5t, e to the 5t. That's one solution. Another solution is the other eigenvector, 3, 4, times e to its eigenvalue times t, e to the minus 2t. All right. Those are independent solutions. The general solution from the theory that we presented is an arbitrary linear combination of any two independent solutions. So we can take these two and say all solutions are y the vector, let's call it y1, y2, equals an arbitrary constant, c1 if you like, times the first solution, e to the 5t, 1, 1, plus an arbitrary constant times the second solution, right? E to the minus 2t, 3, 4. There's the answer to our problem. This is the general solution of a homogeneous system of linear equations. It's C1 first solution plus C2 second solution, where the first solution is e to the eigenvalue t eigenvector, and the second solution is e to the eigenvalue t eigenvector. This works whenever your matrix has two independent eigenvectors. What do we do if they're not independent eigenvectors? There's another technique called the generalized eigenvector we discussed. We can do that in a little bit. Also, even though this gives you all the solutions and when the eigenvalues are complex conjugates, which can happen, in that case you only want the real solutions. We'll discuss a way of reducing to the real solutions. But we'll say for problems like this where you get real eigenvalues and two independent eigenvectors, this always gives you the general solution of a homogeneous system. Now let's look at some inverse transforms. The Laplace transform will show you what I test. Suppose we want to do this one. We want to find the inverse transform. We've looked at this one before. Review it again for the final. Inverse transform of this function, f of s equals 2s over s squared minus 6x plus 5. All right? How can we find that? This is an important kind of problem because these kind of things tend to come up in a lot of engineering applications. Well, L inverse of 2s over s squared minus 6s plus 5. Actually, it's found in a lot of tables of inverse transforms. You can look this up, or you can memorize the simple elementary transforms, and you can do it this way with partial fractions. Even if you do have the table, if you have a higher power denominator, you still need to do partial fractions. So this is a simple example of an important technique in case you have a higher power denominator. All right. Now, how do I rewrite this using partial fractions? We know that 2s over s squared minus 6s plus 5 has a denominator that factors as s minus 5. Gotta be careful, that 5 looks like an S, doesn't it? Times S minus 1. Alright, and therefore by partial fractions you can write this quotient as A over S minus 5 plus B. Make sure this gets in the picture here. Over S minus 1 for some A and B. What can those be? You multiply through, right, by the least common denominator, S minus 5, S minus 1, and you wind up with 2S equals A times S minus 1 plus B times S minus 5. Your calculator, using the expand function and the TI calculators, can also do these partial fractions for you quite easily. Alright, now suppose I carry this over to the right hand side in group like terms, then by subtracting 2s from each side, have 0 on the left, and s multiplies over here, the minus 2 that I brought over, and also a plus b. Then there are constant terms, minus a minus 5b. Alright. And so by collecting like terms, and I observe that if this is equal to 0 on an interval of s values, then it must be that each coefficient vanishes, right? If these coefficients were non-zero, it would be a simple linear equation. A number times s plus a number equals 0, you get one solution. You can't make this vanish on an interval. So you say it must be that a plus b minus 2 equals 0. All right, a plus b equals 2. And minus a minus 5b equals 0, so that means a plus 5b equals 0. And then I can use elimination to solve this system that's equivalent to this, right? Two linear equations, two unknowns. I might just call this equation 1 and equation 2, and then I observe if I take equation 2, subtract equation 1, I can eliminate a, right? This one minus this one, a minus a is 0. 5b minus b gives me 4b. And then 0 minus 2 gives me minus 2. Evidently, b equals minus a half. So I observe here that b equals minus a half. And then I can plug that into either equation. If b is minus a half, then a must be 5 halves. And we can fill in now that by partial fractions, this is 5 halves, and this is minus 1 half. All right, so now I've got my partial fractions written out. I can apply that in here. My inverse transform I want is of equivalently 5 halves times 1 over s minus 5 minus 1 half times 1 over s minus 1. So this inverse transform is equivalent to this one. I want you to be able to do partial fractions for the final exam. Now remember, the Laplace transform and inverse transform are linear operators. That means that the inverse transform of a linear combination is the linear combination of inverse transforms. I can write this as 5 halves inverse transform of 1 over s minus 5 minus 1 half inverse transform of 1 over s minus 1. And, right, we know these are inverse transforms because they're integral. The integral of a linear combination is the linear combination of the integral. All right. This transform is one you memorize from the very simple memorization table we discussed, right? So this is the inverse transform of e to the 5t. We have 5 halves e to the 5t. 1 over s minus a is the inverse transform of e to the at, is where I got this from. I guess I write it down. We have this in the table, that the Laplace transform of e to the at is 1 over s minus a. It follows the inverse transform of, going back the other direction, of 1 over s minus a is e to the at. Is the transform of e to the 5t. This one, similarly, is the transform of e to the 1t. And there we have the function that has this transform. Here's part 2b that you just saw. What if we want the inverse transform of e to the minus s over s squared plus 4s plus 5? This is a different problem. When you can factor the bottom using real numbers, people usually use partial fractions to solve these. What's generally easier, even though partial fractions works, is to instead complete the square. If you use partial fractions here, this factor is only using complex numbers. This is what we call an irreducible quadratic. Right? As squared plus bs plus c with b squared minus 4ac negative is said to be irreducible because you can't factor it over the real numbers. So if I factor this, I have to do complex partial fractions, and then I have a mess trying to figure out what the inverse transform is, even though it works. I'll suggest this instead. When b squared minus 4ac is negative, since you can't factor with real numbers, instead complete the square. Alright, completing the square means I take this part and figure what would I have to add to make this a square. I take 1/2 of this number squared, which is, 1/2 of 4 is 2, squared is 4. I have to have 4 here. So I'll break this up into s squared plus 4s plus 4, a perfect square. Then I have 1 left over to make 5, right? So this is what I wind up with. And now, I can rewrite it like this, suggestively, as the inverse transform of e to the minus, I put suggestively up here 1 minus 1s, e to the minus 1s over s plus 2 squared plus 1 squared. I do that because this looks like something we've seen before. You don't have to put the square on there, obviously. But now, how can I inverse transform this one? It has an e to the minus number times s in it. This is the second shifting theorem, right? The second shifting theorem says that the Laplace transform of the Heaviside step function at t minus t0 times f shifted to t minus t0 is equal to e to the minus t0s times the transform of the unshifted function f of t. Now, put in reverse, the second shifting theorem says that the inverse transform of e to the minus t0s times the transform you recognize, you can look up in the table, can be found as the Heaviside step function at t minus t0 times the unshifted function f of t shifted to t minus t0. That says this is notation for f of t minus t0. So f of t shifted. And so let's do that here. This is equal to h of t minus 1, inverse transform of what's left, 1 over s plus 2 squared plus 1 squared shifted to t minus 1. So that's the second shifting theorem. This is really an excellent review problem for the final. Try this, or something like it, and make sure you can do these, because this has all the, well, most of the stops pulled out here. It doesn't have the convolution theorem and so forth, but has a lot of the important things. I notice here, this is almost the transform that I recognize from the table, and indeed this is actually in the table, but in the big table. But you can do this without the big table, and you need to for other applications do a similar thing. If only it was 1 over s squared plus 1, I would recognize that's the transform of sine t, right? So how can I make it the transform of sine t? I use the first shifting theorem, and the first shifting theorem says that the Laplace transform, maybe I can erase this one, the Laplace transform of e to the at times f of t is the usual transform of f of t shifted. So it's f of s minus a. Call the shifting theorem because now this shifts the graph of f of s over by a units in the complex plane. All right. So let's apply that here and say this is equal to h of t minus 1. This written in reverse says that the inverse transform of f of s minus a is equal to e to the at times the inverse transform of f of s. So let's write it that way and say this is h of t minus 1 times the times this part is now e to the negative 2t because minus 2 is being subtracted here, right? Times the inverse transform of this without the shift. 1 over s squared plus 1. So that's the first shifting theorem. Doesn't matter what you call first or second. Now, what's the inverse transform of 1 over s squared plus 1? We recall from our basic transforms that that's sine. So this is h of t minus 1 e to the minus 2t. And I forgot to put something on here. This all has to be evaluated at t minus 1. E to the minus 2t sine t shifted to t minus 1. So the final answer then is h of t minus 1 times all this with t replaced by t minus 1. E to the minus 2 t minus 1 sine of t minus 1. There it is, the inverse transform. Now, the Laplace transform to solve the differential equation. The old techniques we had couldn't solve differential equations that had step functions like this in them. You looked at this exact problem before. Let's look at it just for review for the final exam. Here I have y prime minus 9y equals u2 of t, where this denotes the Heaviside step function. This is another notation I wanted you to be familiar with. It's common. This denotes h of t minus 2, so you can replace that if you like, or you can leave it like this, whichever notation you prefer. It's the step function like this at t, for t less than 2, it's equal to 0, right? And then at t equals 2, it jumps up here to 1. So it's a unit step at t equals 2. That's what that is. And engineers draw it like this, meaning the same thing. If we want to solve this differential equation where maybe you have a circuit or something and at time t equals 2 you suddenly apply a voltage to this circuit, you get a unit jump in voltage from 0. What is the solution to this? Well, we said that you can take the Laplace transform. This is how you solve a differential equation. You take the Laplace transform of both sides. You solve the resulting algebra problem because it converts a differential equation into an algebraic equation. Then you inverse transform the solution of the algebraic equation. It's a 1, 2, 3 method, we said, right? So we'll take the Laplace transform of y prime minus 9 times the Laplace transform of y. That's the Laplace transform of the left, right? Because the Laplace transform of the linear combinations, the linear combination of Laplace transforms. That has to be equal to the Laplace transform of the right, u2 of t. Now, this one we recall from the theorem for differential equations, or derivatives, is sy of s, where y of s denotes the Laplace transform of y, minus y of 0. So there's the Laplace transform of y prime. Then I need to subtract off 9 times the Laplace transform of y. I'll just change notation and call that y of s. It means the same thing. And then the Laplace transform of u2 of t, well, it's like that suggestively h of t minus 2. What is that? Well, we have a theorem that says the Laplace transform of h of t minus t0, f of t minus t0 is equal to e to the minus t0s f of s, where f of s is the transform of the unshifted function f of t. So we need to apply that, but we just have h of t minus 2, right? Oh, just multiply it by 1. All right, so f is the function 1, and there's no t in it, so as shifting it doesn't change it, right? It's still a horizontal line. So we must have e to the minus 2s times the transform of 1 is 1 over s. All right, so there's the transform of this equation using the second shifting theorem. Now y of 0 is equal to 1, so we can put that in. And there is the transform of the differential equation. Now, step 2, you have an algebraic equation at this point, so you want to solve algebraically for y of s, the transform of the solution. So let's see, here's s y of s, and here's minus 9y of s. So s minus 9y of s. And then I'll collect all the other terms over on the other side. Equals 1 plus e to the minus 2s over s. That's just algebra at that step. Now divide by s minus 9, you get finally that y of s is 1 over s minus 9 plus e to the minus 2s over s times s minus 9. Right. That's step 2. Step 3, you take the inverse transform. Y of t, the solution of this initial value problem. Right, differential equation with an initial value is an initial value problem. And y of t is the inverse transform then of 1 over s minus 9 plus the inverse transform of e to the minus 2s over s times s minus 9. So we just need to do that, and our solution to this differential equation pops out. So solving differential equations by the Laplace transform is as easy as 1, 2, 3, right? Just have to remember those 3 steps. Y of t equals, well, what's the transform of 1 over s minus 9? Remember, the transform of 1 over s minus a is the transform of e to the at, so this must be e to the 9t here. Right? Now over here it's a little more difficult, but we recognize that e to the minus 2s has a function. We can rewrite that as h of t minus t0. Right? E to the minus t0 s comes from h of t minus t0 times the inverse transform of what's left, also shifted to t minus 2. So that's the second shifting theorem again. And how do I find this one? Since there's factors with real numbers, I can use partial fractions. Now maybe I go to my calculator or I quickly do it by hand. I say 1 over s times s minus 9 is some number over s plus some number over s minus 9. We won't do all the partial fractions again. We'll simply say that it's that it turns out that a is minus a 9th and b is plus a 9th. So with that in mind, we can say that y of t, the solution to this differential equation and initial value, is the inverse transform of minus a 9th 1 over s plus a 9th 1 over s minus 9 shifted to t minus 2 at all times h of t minus 2. All right. Well, these are transforms we've memorized though, right? The minus 1/9 comes out. inverse transform of 1 over s is just 1. The 1/9 comes out. And the inverse transform of 1 over s minus 9 is e to the 9t. And then I just have to shift this part to t minus 2. I should put this in brackets, not this part. Well, this one shifted to t minus 2. There is no t, so it's still minus a 9. And this one, you just replace t by t minus 2. It's e to the 9 t minus 2. There's the solution to this initial value problem. Well, let's try taking some Laplace transforms. If f of t is this piecewise defined function, or g of t is this piecewise defined function, how can we do them? Well, remember we have the theorem that says the Laplace transform of a piecewise defined function can be calculated using the Heaviside step function. So we're going to rewrite this as h of t minus 3, t minus 3 cubed. And what we're thinking here is that this is f of t minus 3 for the unshifted function, f of t equals t cubed, right? If f of t is t cubed, this is f of t minus 3. And remember, we have the Laplace transform of h of t minus t0. This is the theorem. F of t minus t0 is e to the minus t0s f of s. So if you have a Heaviside step function, how's a function shifted by the same amount? You get e to the minus shift s times the transform of the unshifted function. So for this one, we'll say the unshifted function was t cubed. What we want here is h of t minus 3 times the Laplace transform, not of t minus 3 cubed, but of t cubed. Well, t cubed, remember, has transformed, t to the n has transformed n factorial over s to the n plus 1. So this one has transformed, t cubed has transformed 3 factorial over s to the 4. And we can replace 3 factorial with 6. And there's the Laplace transform of this function. A little harder one here. Suppose I have a function that's periodic. These are important in lots of signal analysis, right? G of s, the transform of this function. We have this theorem that the Laplace transform of a periodic function of period capital T is the integral taken in the usual way, except instead of going from 0 to infinity, you just go from t to the period. If the period is capital T, then you go from 0 to t instead of 0 to infinity. The usual Laplace transform, e to the minus st f of t dt. So in other words, you take the Laplace transform over one period, and then you divide it by 1 minus e to the minus s times the period. There's the Laplace transform, so we'll apply it to this one, and we'll say if it's period 2, this is the integral from 0 to 2 of what would have been the Laplace transform of this function, t over 2, and divide it by 1 minus e to the minus 2s. And I'll say you can pull this 1/2 out and rewrite this as integral from 0 to 2 t e to the minus s t dt over twice 1 minus e to the minus 2s. And then this one falls to integration by parts. About a power series problem. Suppose I want to solve this differential equation, which you already know how to solve by method of characteristic equation, right? You can write the characteristic equation r squared minus 4 equals 0, with solutions plus or minus 2. So c1 e to the 2t plus c2 e to the minus 2t is the general solution of this homogeneous equation with constant coefficients. We can also do it by power series methods. Power series methods are really designed for non-constant coefficients, because you'll see it's much harder than solving this equation this way. And sometimes the power series you get doesn't converge on as large an interval as this kind of solution. But we studied them for when maybe you have a t or a t minus 1. If you have simple coefficients here that are not constants, the power series method may provide you a solution to those with more work than we're going to do here. Let's solve this one as an example of using the power series method and simply say its purpose is to apply to other differential equations that don't have constant coefficients, to give you a little bit of other equations you can solve, right? The Laplace transform method also works for some of those if they're not too terrible. Let's try this one. The power series method means you write y as a power series. Let's use a power series at t equals 0. That's the easiest one. Solve using a power series t0 equals 0. Well, a power series, you recall, is a series like this, ak t minus t0 to the k equals 0 to infinity. Right. There's our power series in general. Now, this gets to be a lot of writing. The easiest power series is when you choose t0 equals 0. Then this reduces to t to the k. So let's look for a power series of that form that gives us the general solution of this equation. If we choose this for the power series, then recall that the derivative of a power series within its radius of convergence is the term-by-term derivative. So this one has a derivative, since we know it converges. We know there's a power series solution, so it's going to converge. At least locally, we don't know what the radius is. And the derivative is just ak as a number times the derivative of t is k, t to the k is k t to the k minus 1. So there's the derivative, except that the k equals 0 term is a constant, right? A0 times 1, when t to the 0 is 1. The derivative of that one is a constant, so actually we have to put k equals 1 to infinity, the derivative of the first term being 0. And then all the rest of these are correct. And we also need y double prime, because that's the differential equation. We take the derivative of this one term by term. And then the derivative of t to the k minus 1. Maybe I better put this over where you can see it, huh? Is k minus 1 t to the k minus 2. Except that the very first term, a1 times 1 times t to the 0, is a constant. Its derivative is 0. So you have to start this at k equals 2. So y double prime, and then after that all these are correct. Y double prime is this one. All right. So now we plug those into the differential equation. That's the power series method, is to plug power series with its derivatives into the differential equation. You then get a recurrence relation for the coefficients, and when you solve that recurrence relation, you have the coefficiency of the solution. That's the power series method. Just plug in and see what the coefficients have to be. So here we'll plug in the second derivative, sum k equals 2 to infinity, ak k minus 1, t to the k minus 2, minus 4 times the function y, sum k equals 0 to infinity, ak t to the k has to equal the 0 function. So there is what we plug in. And now, in order to solve for the coefficients, we're going to have to try and combine these series. To combine the series, we need them to run over the same indices and with the same power of t. Well, this one has t to the k, and this one has t to the k minus 2. So I'm going to make a substitution here. I'm going to let n equal k minus 2. So that k equals n plus 2. And this one, I'm just going to let n equal k. And I can do this because now when I finish here, this will be t to the n, and this will be t to the n. I'll have achieved the same power of t in each of these. And I could do this because k is just a dummy index, right? This sum here means a0t to the 0 plus a1t to the 1 plus a2t to the 2. I can change this to n or p or whatever I want. And it'll be the same sum as long as I sum over the right indices. Now when I do this, n is equal to k minus 2, so when k equals 2, n is equal to 0. So this now starts at n equals 0. Then I will make the same sum as I had here. I have to, I'll just replace the dummy index k with the new dummy index n, and n goes from 0 to infinity, sums over the same things. All right, and now ak becomes a n plus 2, k becomes n plus 2, all right. K minus 1 is 1 less, it's n plus 1, and t to the k minus 2 is t to the n. So that's the first series, rewritten with a new dummy index. And then I'm going to subtract this series, and moreover, I can pull a constant in, right? A constant times a series is the same as multiplying each term in the series by the constant. It's just a distributive law applied to an infinite number of terms, right? This is 4 times a0 plus a1t plus a2t squared plus dot, dot, dot is what I've written here. And you just pull a 4 in, and it becomes 4a0 plus 4a equals. So it's a distributive law applied to an infinite number of terms. Turns out to be a theorem from calculus. So I'll pull the 4 in, and then I'll just replace k with n straight through. So this is minus sum n equals 0 to infinity, 4a(n) t to the n, all equals 0 on the right-hand side. And I'm going to do something with the right-hand side here that will help make this clear what we're doing. 0 has as its power series n equals 0 to infinity. 0 times t to the n, right? These all add up to 0, so this is a power series for 0. Now, moreover, you have to remember from calculus that power series representations are unique. When I have a power series, there's only one set of coefficients that can be there. If I change even one coefficient, it won't add up to the same thing everywhere. So for convergent power series, which these are because the differential equation has a power series solution by our theorem that we had, we know that the coefficients on the left match the coefficients on the right. So I'm going to write equivalently by combining these two, and look, they now go from 0 to infinity, both of them, with the same power of t, so they can be combined term by term. I remember this, the theorem that says sum a(n) t to the n plus sum b(n) t to the n is equal to sum a(n) plus b(n) t to the n over the same set of indices. Whenever you have convergent power series, you can combine them term by term like that. So we'll combine this and say this is a(n) plus 2 times n plus 2 n plus 1 plus, minus 4a(n) all multiplied by t to the n. That's combining these first two series into one. All right? This is the theorem that we just erased here. Is all equal to the right-hand side, sum 0 times t to the n. And now we've got our recurrence relation, because when two power series that are convergent are equal, they match term by term. Each of these has to be equal to 0 to match the 0 over here. That's our recurrence relation. a(n) plus 2 times n plus 2 times n plus 1 minus 4a(n) must be equal to 0 for each n in here. N equals 0, 1, and on forever. Now what we can do is we can inductively figure out what these ANs are. That is, we see a pattern going and deduce from the pattern what the formula is. So we'll rewrite this by adding 4an to each side and dividing by n plus 2, n plus 1, that an plus 2 is actually equal to plus 4an over n plus 2, n plus 1. Just algebra, right? Add this over and divide by this. And now I can make a table. And I'm going to break this up into two pieces, one for n even, and I'm going to write n down here, and then an here. And then I'm going to make another table over here for n odd. Now look at the an's here. So if n is equal to 0 or 1, actually this is arbitrary. This applies for n equals 0, 1, 2. So A0 and A1 are not determined by this, but then A2, when you put n equals 0, is determined by A0, right? A0 over here determines A2 on the left. When I put in n equals 2 here, it determines A4 on the left. When I put A4 here, it determines A6 on the left. That's why I broke this into even and odd. The evens will all be determined from A0, and similarly, if I put A1, that will determine A3, A3 will determine A5. The odds will all be determined by A1. So A0 and A1 are arbitrary, and then, if you put n equals 1 in the equation, maybe I should not list n over, but if I put n equals 1 in the equation, then I get A3 on the left equals 4A1, oops, sorry, evens. Put n equals 0 in the equation, A2 on the left equals 4A0 on the right over 0 plus 2, 0 plus 1 is 2 times 1. Alright, now that's putting n equals 0 in the equation. If I put n equals 2 in the equation, I get A4 on the left equals 4A2 over 4 times 3. And you can start to see a pattern going, right? A6 is now 4A4 over 6 times 5. And you can say, wait a minute, A2 is given by 4A0 over 2A1, so I can rewrite this as 4 times 4 times A0 over 4 times 3 times 2 times 1, putting this for A2 in here. And then similarly, this is just 4 squared now, right? Now 4 times A4 is 4 times 4 squared is 4 cubed, times A0, all over 4, 3, 2, 1, and 6, 5. 6, 5, 4, 3, 2, 1 all multiply together. We can deduce inductively what we're getting, right? For the first, second, third, fourth. Well, each one of these powers is just 1/2 of this. Let's see. 1/2 of this. 4 of the first for 2, 4 of the second for 4, 4 of the third for 6. I deduced that an is 4 to the n over 2. Right? Times a0 all over 1 through 6 for 6 factorial, 1 through 6 factorial, 1 through 4 is 4 factorial. For an, I must be getting n factorial. So 4 to the n over 2a0 n factorial is the coefficient formula when n is even. How about when n is odd? We can similarly do this. When I put n equals 1 in here, I get a3 is 4a1 over 3 times 2, with putting in n equals 1. Similarly, a5, by putting in n equals 3, a5 is 4a3 over 5 times 4. And you can do this for some more, but you might be beginning to see already that the nth term when n is odd is equal to 4, well, let's rewrite this one in terms of a1, that's 4 squared times a1 over 5, 4, 3, 2, putting in what a3 is in the first step. Maybe you can see the pattern already. If not, just do another term, right? But what I'm going to get is, for 3 I get first power, for 5 I get second power, for 7 I get third power. It must be that I've got 4 to the n minus 1 over 2 is the power, right? So if I put in n equals 3, I got 3 minus 1 over 2 is 1 for the first power. If I put in 5, I get 5 minus 1 over 2 is 2 to the second power, and so on. So I get first power, second power, third power, and so forth. All times a1 over, for 5 I get 5 factorial, for 3 I get 3 factorial, I deduce it must be n factorial in general. Here are the coefficients when n is odd. Now I have the solution, right? Because the solution is just a power series a n t to the n. And I found formulas for all the a_n's, except a0 and a1 are arbitrary. So I write now the solution to the differential equation is just y equals sum a n t to the n. Our initial assumption, which was valid for this kind of a differential equation, it does have such a solution, must be, well, here's what you can do with power series. Within their radius of convergence, you can break them up into sums. N equals 0 to infinity, n even, a n t to the n, plus sum n equals 0 to infinity, n odd, a n t to the n. And that's your properties from calculus, one of your properties. But when n is even, I have this formula, so this is sum n equals 0 to infinity, 4 to the n over 2, a0 over n factorial, e to the n. So I put in the formula now for an when n is even here. Oops, and this should have been from n equals 1 to infinity n odd. This is sum n equals 1 to infinity n odd. And formula here is 4 to the n minus 1 over 2, a1 over n factorial. There we have actually the general solution of this differential equation. How can you see that it's the general solution? It's pretty easy, and you would think so since we haven't made any assumptions on initial conditions. This would be the general solution. But here's how you can show it. Pull a0 out of this one, right? You can pull a constant out. This is sum n equals 0 to infinity. 4 to the n over 2 over n factorial, e to the n. This one you can pull a1 out. It's just a constant. So you pull constants out of these series. And this is n equals 0 to n evens, right? This is n equals 1 to infinity, n odd. Four to the n minus 1. I forgot my t to the n here. T to the n over n factorial. And these are all solutions. We got them by plugging in, shows that they're solutions, no matter what a0 and a1 are. So let's put a0 equals 0 and a1 equals 1. Then we get this series is a solution, right? We've proven that this is a solution. All right. Now suppose I put a0 equals 0 and a1 equals 1. We've proven that this is a solution, because these are all solutions. So this series is a solution. This series is a solution. This represents an arbitrary linear combinations of two independent solutions. Independent because this is an even function having only even powers of t. This is an odd function having only odd powers of t. So we've got an arbitrary linear combination of two independent functions. It must be, by theorem, the general solution, right? That was our theory for homogeneous equations with constant coefficients, or with continuous coefficients even. So this is the general solution. However, we don't like to leave it here. Typically, we like to rewrite this. Let's put this back with another substitution. We can use any dummy glitter we want. We can use k again with even a different substitution. Let's let n equal 2k, so that k equals n over 2 in this one. Then we can rewrite this series a little nicer. This is a0 times sum. If k is n over 2, then n running over the even k runs over all the non-negative numbers. K runs from 0 to infinity. 4 to the n over 2 becomes 4 to the k. N factorial becomes 2k factorial. T to the n becomes t to the 2k. Now the series is cleaner, right? It just runs over all whole numbers, 0, 1, 2, 3, up to infinity. And this one has A1 multiplying on the outside, and if we make a substitution here, N equals 2K minus 1, so that K, let's see, no, it's 2K plus 1, so that K equals N minus 1 over 2. And my apologies, this should have been N minus 1 over 2, I just copied it. This is some K running from 0 to infinity, right? When N equals 1, that puts K equals 0. When N equals 3, that puts K equals 1. So as N runs over the odds, K runs over all the whole numbers. And then 4 to the N minus 1 over 2 becomes 4 to the K. N factorial becomes 2K plus 1 factorial. Let's see. Yeah, and then T to the N becomes T to the 2K plus 1. There we go. Here's the clean way to write the general solution. As clean as a power series you can get anyway. It's an arbitrary constant times this series plus an arbitrary constant times that series. Here's an interesting problem with a mass on a spring. If I have a 32-pound mass, it extends the spring 0.32 feet from its unweighted equilibrium position, and the mass is initially 1 foot above hanging equilibrium and has initial velocity 2 feet per second downward. What is its motion? So we draw this picture, and let's put u downward just for convenience. You can put it upward and just get the same results, but we'll choose the convention u, the displacement is downward. So it starts 1 foot upward above equilibrium. We deduce in these that at time 0, the position is minus 1, right? Against the direction of positive u. Initial velocity 2 feet per second downward, that's the positive direction, so u prime of 0 is equal to 2. So we'll write down those initial conditions. And now, what about the equation of motion? We have this equation of motion for a mass on a string, right? M d squared u dt squared plus c du dt plus ku equals f of t, where f is a forcing function of some sort. You write down this general equation, and then you say, wait a minute, there's no damping involved here, right? So this term is 0. C must be 0, 0 damping. And there's no forcing function, right? We're not pushing it with some external force. So this one's 0. That means that for this case that we've written up, we have that m d squared u dt squared plus ku equals 0. This is the simple harmonic motion case, it turns out, right? But that's it. Where this equation comes from, remember, is you can rewrite it like this. Put these over on this side by putting a minus on them. And what we're saying is that mass times acceleration, Newton's law, is force, and we just sum the forces, right? The force of damping proportional velocities minus c du dt for some positive number c, minus ku is the spring force, and f of t is any additional force we apply as a function of time. So that's where this equation came from. But you memorize the equation, and then you get this special case when there's no damping and no forcing function. But what are m and k? Well, it's a 32-pound mass, right? From the 32 pounds, we deduce that the force of gravity on it, 32 pounds, is m, the mass, times g, 32 feet per second squared is the acceleration of gravity. Oh, this just says m equals 1. So it's a one slug mass. English unit pounds is a force. The mass here is in slugs. Now we also know that if we hang it on the end of the spring, it extends the spring 0.32 feet. So we say 0.32 feet, the extension, times the spring constant K. It's a Hooke's law spring, we're assuming. K times 0.32 is the force of the spring. Is that exactly balancing gravity? 32 pounds, the weight of the spring. So if we hang the spring like this, 32 pounds downward from gravity, that exactly balances K times the displacement that it did, 0.32. That tells us that K is 32 divided by 0.32, or K is 100. So we have M equals 1, K equals 100. In this equation, we write down the equation of motion is 1 d squared u dt squared plus 100 u equals 0. And then we have the initial conditions. U of 0 is negative 1. U prime of 0 is 2. How do we solve this one? We write the characteristic equation, right? This is a homogeneous equation with constant coefficients, so we just solve the characteristic equation, r squared plus 100 equals 0. We observe that then r, the two values, r1 and r2, plus or minus 10i. Alright, because r squared is negative 100. That means that solutions are u1 is you call it 0 plus 10i, e to the 0t cosine 10t, or just cosine 10t. And u2 is e to the 0t sine 10t, this is from r2, r1 and r2, is just sine 10t. Therefore, the general solution, u, is an arbitrary linear combination of c1 cosine 10t plus c2 sine 10t, and we can get its derivative also. U prime is then minus 10 c1 sine 10t plus 10 c2 cosine 10t. Now we can plug in the initial conditions. U of 0 is minus 1 plugs into this one, and we get minus 1 is equal to c1 cosine 0 is 1 plus c2 sine 0 is nothing. We have found that c1 is negative 1. How about c2? We have that from the derivative that 2, right, new prime of 0 is 2, is equal to this evaluated 0, minus 10 c1, well that's minus 10 times negative 1, plus 10 c2 cosine, oops, I'm sorry, this is sine of 0. 2 is equal to 0 because sine of 0 is 0, plus 10 c2 cosine of 0 is 1. So the second initial condition, u prime of 0 equals 2, says 2 equals 10 c2, plugging it in here. So c2 is equal to 1/5, and putting those into the general solution then tells us that u must be minus 1 cosine 10t plus 1/5 sine 10t. Well, here's an equation that's kind of interesting. It says solve for this x is a function of y because it becomes linear. Here's what you do. You can divide by dy to get a function for dx dy. So this is y dx dy minus 2 x plus y to the 6 equals 0. Now if I divide through by y to put it in standard form, I've got dx dy minus 2 over yx minus 2y to the 5th equals 0. Dividing by y. And now I recognize by putting 2y to the 5th on the right hand side that this is dx dy plus negative 2 over yx equals 2y to the 5th. This equation is a linear equation for x as a function of y. I'll put this in here just to show you a little abstraction of solving linear equations for y as a function of x. This is a function p of y. This is a function f of y, and so it's the same thing you saw before, dy dx plus p of xy equals f of x, except with x and y interchanged. So remember how to solve a linear equation. I'll certainly have a linear equation somewhere that you have to do on the final exam. You substitute, or you find an integrating factor, mu equals e to the integral p of x dx, except this time it's p of y dy. It's e to the integral of minus 2 over y. Well, let's see, that's e to the minus 2 ln y plus a constant if you want, but we only need one integrating factor, so it doesn't matter. And now this is e to the minus ln of y squared. Absolute value of y squared is the same as y squared. And so, oops, should be the minus 2. And 1 over y squared is the same as 1 over absolute value y squared. So we drop the absolute value. And e and ln undo each other. This is just 1 over y squared. So what I need to do is either multiply this equation through, that's in standard form, by 1 over y squared, or I can go straight to the formula. If you go straight to the formula, make sure it's in standard form first, put 1 as the leading coefficient. Right? That's a common error to not do that. Alright, in fact, when you compute mu, you need to do that. But the solution is that x equals 1 over mu integral mu f dy this time. We just interchanged x and y again. Mu was 1 over y squared, so 1 over mu is y squared. F is the right-hand side, 2y to the 5th. And there's our general solution to this linear differential equation for x as a function of y. We've got y squared times twice the integral of y cubed dy. Well, integral of y cubed is y to the 4th over 4. So we have y squared over 2 y to the 4th plus a constant, an arbitrary constant from the integration, gives us 1/2 y to the 6th plus, what do you call this constant? 2c, it's an arbitrary constant, then it's plus c times y squared. There's a nice way of expressing the general solution. Well, number 9 is an integrating factor. Suppose I want to find an integrating factor for this equation. Remember how you do that? We only learned 2 types of integrating factors. There's more general ones, but they're seldom as useful. If we want to find an integrating factor that's a function of x only, I can look for my minus nx over n. And if that's a function of x only, then there's an integrating factor that's a function of x only. nx minus my over m. If that's a function of y only, then there's an integrating factor that's a function of y only. So we try it. nx partial with n with respect to x is y, minus my partial with respect to y is 4y, all over m. Well, that's not a function of y only, so no u of y. But we can try my minus nx over n. We've already computed these, 4y and y, and then n is xy. 4y minus y over xy. Well, let's see, that's 3y over xy, and the y's cancel. 3 over x is a function of x only. There is an integrating factor that's a function of x only, and it is u of x equals e to the integral of whatever you got here, 3 over x. Well, this is e to the 3 natural log x, which is e to the ln of x to the 3rd is x to the 3rd. Well, I say absolute value of x to the 3rd, but really ln isn't defined at x equals 0 anyway, so we can take x to the 3rd as an integrating factor on the interval 0 to infinity or minus infinity to 0, it doesn't matter. And multiple of an integrating factor is an integrating factor, so we'll just say x cubed is an integrating factor on either interval. And if we multiply this through by x cubed, it will become integrable. Let's try 2x cubed y squared plus 3x to the fourth, now multiplies dx, plus x to the fourth y, now multiplies dy. And the new m, we can call it m hat if you like, and the new n hat, let's see if this equation is now exact. My equals partial with respect to y is 4x cubed y. And x, partial of this with respect to x, is 4x cubed y. Sure enough, it's exact. I can now solve it by the method for exact equations, but the question is just find the integrating factor. Apparently, an appropriate integrating factor is u equals x cubed. So number 9 is an integrating factor. Suppose I want to find an integrating factor for this equation. Remember how you do that? We only learned 2 types of integrating factors. There's more general ones, but they're seldom as useful. If we want to find an integrating factor that's a function of x only, I can look for my minus nx over n. And if that's a function of x only, then there's an integrating factor that's a function of x only. Nx minus my over m, if that's a function of y only, then there's an integrating factor that's a function of y only. So we try it. Nx partial of n with respect to x is y, minus my partial with respect to y is 4y, all over m. Well, that's not a function of y only, so no u of y. But we can try my minus nx over m. We've already computed these, 4y and y, and then n is xy. 4y minus y over xy. Well, let's see, that's 3y over xy, and the y's cancel. 3 over x is a function of x only. There is an integrating factor that's a function of x only, and it is u of x equals e to the integral of whatever you got here, 3 over x. Well, this is e to the 3 natural log x, which is e to the ln of x to the third is x to the third. Well, I say absolute value of x to the third, but really ln isn't defined at x equals 0 anyway, so we can take x to the third as an integrating factor on the interval 0 to infinity or minus infinity to 0, it doesn't matter. And multiple of an integrating factor is an integrating factor, so we'll just say x cubed is an integrating factor on either interval. And if we multiply this through by x cubed, it will become integrable. Let's try 2x cubed y squared plus 3x to the fourth, now multiplies dx, plus x to the fourth y, now multiplies dy. And the new m, we can call it m hat if you like, and the new n hat, let's see if this equation is now exact. My equals partial with respect to y is 4x cubed y. And x, partial of this with respect to x, is 4x cubed y. Sure enough, it's exact. I can now solve it by the method for exact equations, but the question is just find the integrating factor. Apparently, an appropriate integrating factor is u equals x cubed. Here's an equation that I'm telling you is homogeneous. This is a different kind of homogeneous, recall, than that for linear equations. This is an equation where the right side function is homogeneous at degree 0 in the function space. That's where that name comes from. So if I have 13, y prime equals y minus 2x over y plus x. How can I solve this by the method for homogeneous equations? Remember the method here? When the equation is homogeneous, you just make a substitution. V equals y over x, so that xv equals y, and by taking the product rule here, v plus x dv dx is equal to dy dx. So we'll make that substitution, replace dy dx with v plus x dv dx, and replace over here y over x with v. Well, I better first write this. So what I can do, let's divide top and bottom by x and say that this is equal to y over x minus 2 over y over x plus 1. Then this is v minus 2 over v plus 1. Now I've got an equation in terms of v and x instead of y and x. So what can I do with this? I'm going to subtract v from both sides and say x dv dx is equal to v minus 2 over v plus 1 minus v. Right? Now the thing about this homogeneous equation is when you make this substitution, it always makes it separable. So that's what you're aiming for. How can I separate variables? All right, v as v times v plus 1 over v plus 1. And now, let's see, I've got v here and I've got minus v here. Let's cancel. That'll simplify it a little bit. I've got x dv dx equals minus 2 plus minus v squared all over v plus 1. Now I see how to separate variables. I multiply both sides by the reciprocal of this and by 1 over x. I wind up with v plus 1 minus over v squared plus 2 equals 1 over x dx. Variables are separated, so I can integrate each side. This one can be integrated by using partial fractions. Remember calculus. Well, actually, I'm sorry. Appropriate ways to split it up. Let's rewrite this as minus integral of v over v squared plus 2 dv plus or minus integral 1 over v squared plus 2 dv equals this side is natural log x. And there's an arbitrary constant, but we can leave it to come out of these integrals. This one can be attacked by u substitution. Let u equal v squared plus 2 du equals 2v dv, and you can integrate this using a logarithm. This one directly, almost directly, can be done by a substitution. W, let's say square root 2w equals v. So that v squared is 2w squared. Then this becomes an integral 1 over 2w squared plus 2 dw of, let's see, and then this should have been dv, let's see, dv from here. And then dv gets replaced by square root 2 dw. And this one comes out to be an arc tangent, right? This is 1/2 the arc tangent w. And then you can do this one by a substitution. Suppose we want to find the inverse transform of this function by the convolution theorem. Since I notice it's a product of two transforms I know, right? This is the Laplace transform of e to the 1t. Laplace transform of e to the at is 1 over s minus a. And this is the Laplace transform of sine 3t, right? Since the Laplace transform of sine at is 1 over s squared plus a squared. I'm sorry, a over s squared plus a squared. I guess this is 1/3 Laplace transform. So this one we could say, if we rewrite it as 1/3 3 over s squared plus 3 squared. We can say this one is the Laplace transform of e to the t, and this is the Laplace transform of sine 3t. Then f of t, the inverse transform, is 1/3 the inverse transform of 1 over s minus 1 times 3 over s squared plus 3 squared. But this being the transform of e to the at, and this being the transform of sine 3t, the inverse transform is the convolution f with g, where f of t is e to the t, and g of t is sine 3t. The convolution is defined to be the integral from 0 to t of f of t minus tau, so we can take a of t minus tau, e to the t minus tau. G of tau is sine 3 tau, d tau. There's the convolution theorem to evaluate that one. Then you can do this one by pulling the e to the t out, because t is a constant with this integral within the integral over tau. So this is e to the t over 3, the integral from 0 to t of e to the minus tau sine 3 tau d tau. This appears in your standard integration tables, but it falls to 2 integration by parts if you want to try your calculus hand with this. Now number 16 here is a different kind of equation. It's an Euler equation. I'll show you how to solve these today. These are related to the equation with constant coefficients. You just make a change of variable by a substitution. Consequently, the method is almost identical. Here it is written out. Suppose I have this Euler equation. An Euler equation is any equation of the form. It can have higher order too, but a second order Euler equation is ax squared y double prime plus bxy prime plus cy equals 0. Any equation that looks like that can be solved in complete analogy to what we did for constant coefficients by substituting, instead of y equals e to the rx to get a characteristic equation, substitute y equals x to the r to get a characteristic equation. And when you put that in, y equals x to the r, y prime is then equal to r x to the r minus 1, and y double prime is equal to r times r minus 1 times x to the r minus 2. So when we plug that in, we've got let's do the actual one here. We've got x squared times y double prime is r minus 1 x to the r minus 2. And then minus 3x is going to multiply y prime, which is r x to the r minus 1. And then you plug in 3 times x to the r is y. Now I've got an equation here. If I multiply this all out, or divide this through by x to the r, here's x to the 2 times x to the r minus 2 is x to the r. I'm left with just r times r minus 1. Then x times x to the r minus 1 is x to the r. Divide through by that, I'm left with minus 3r. And then plus over here, divide by x to the r, I'm left with plus 3 equals 0. This is the characteristic equation for the Euler equation. If you were to make the substitution of variables, you can get a constant coefficients equation and a substitute variable, and this would be its characteristic equation for the constant coefficients case. Now, we multiply this out, we've got equivalently r squared minus 3r minus 3 more r is minus 6r, and then plus 3, minus 4r. plus 3 equals 0. This factors nicely, right? R minus 3 times R minus 1 equals 0. That says there are two values of R. R1 equals 3 or R2 equals 1. Now what we did, our ansatz, our assumption here, is that there's a solution form x to the R. There's a solution form x to the R we showed if and only if R is 3 or 1. Well, that says those are two solutions. Therefore, one solution is y equals x cubed, and another solution is y equals x to the first. That's what we just showed. Well, we remember for these second order equations with continuous coefficients, the general solution is the arbitrary linear combination of any two of them. So the general solution is y equals c1x cubed plus c2x. Well, let's try a higher order equation with constant coefficients like y to the fourth derivative. Usually we put this parentheses 4 for fourth derivative because these hash marks get to be too many. After a while you can't count them. Plus y equals 0. Suppose I want to solve that fourth order differential equation with constant coefficients. What's its general solution? Well, we write the characteristic equation, right? R to the fourth plus 1 equals 0. Now, how do I find the solutions of that? You can use complex numbers and you say R to the fourth has to be equal to minus 1. Now, minus 1 can be written in terms of complex numbers as 1 times e to the I pi, right? The idea is that you write it as r e to the I theta in the complex plane, where this is the real part of r and this is the imaginary part. So this is the r equals alpha plus I theta plane. And if you have minus 1, it's over here. Minus 1 plus 0i in the complex plane, right? You put the real part on this axis and then you move the imaginary part that way. So minus 1 plus 0i is here. It's in an angle theta equals pi. And at a radius out, r equals 1 is how you compute that, right? So it's 1 e to the I pi. Any number can be written, any number z can be written as r e to the I theta by this construction. Go to the angle on the complex plane. And then all other ways of getting there, you can add a multiple of 2 pi. So we can put plus 2k pi can be added to that angle and you'll get to the same spot. So I'll write, say this is e to the I pi plus 2k pi. These are all representations of the number minus 1 in polar form. This radius, any of these angles. And k can be any integer, 0, 1, minus 1, 2, minus 2, and so on. And r to the fourth has to be that. So if we take the fourth roots, we find that r has to be the fourth roots of this is 1 to the 1/4 times e to the angle divided by 4, right? The fourth root of this is this over 4. And so now, what is r? Well, it's 1, fourth root of 1 is 1, times, you can now go to any one of these angles. And so these angles, you have radius 1 and angles pi over 4 plus k pi over 2. And so those are all the fourth roots of -1, we call them. In the complex plane, alpha plus I theta is r. We can go to an angle pi over 4 here and out 1 unit. And what number is that in the complex plane? Well, we went over here, 1 over square root 2, and over here, 1 over square root 2. So this is the number 1 over square root 2 plus 1 over square root 2i. Now we can add pi over 2 to that and get over here. Now this is 1 unit out at an angle 3 pi over 2. that complex number, by dropping a perpendicular, is 1 over square root 2 this way and 1 over square root 2 this way. But this is negative, so this is minus 1 over square root 2 plus 1 over square root 2I. Then we can go pi over 2 more around to this angle, and we've got 4 multiples of pi over 2, and then they start repeating. So there's an infinite list here, k equals 0 to infinity and minus infinity, but only 4 different directions in the complex plane. So out of these, we can really just look at k equals 0, 1, 2, and 3, and then they start repeating. Well, you'll just get to the same points. So this one's 1 unit out, and you go minus 1 over square root 2, minus 1 over square root 2. This is the point minus 1 over square root 2, minus 1 over square root 2I. This one here, 1 unit out, and pi over 2 more over, goes, since this is 1 unit out, this is 1 over square root 2, well, this is 1 over square root 2. This is number 1 over square root 2, minus 1 over square root 2I. Those are the 4 values of R. This is, if you like, R1, this is R2, this is R3, and this is R4. That tells you exactly what your solutions are going to look like, right? When you have complex conjugate pairs here, I have 1 over square root 2 plus 1 over square root 2I and minus 1 over square root 2I. Those correspond to solutions. Y1 equals e to the 1 over square root 2I, the real part I, times cosine 1 over square root 2I, t. And y2 equals e to the 1 over square root 2t sine 1 over square root 2t. Remember, complex conjugate pairs like that have corresponding pairs of real solutions like that. And then for these, with minus 1 over square root 2 each, and then plus or minus the imaginary part, you get y3 is e to the minus 1 over square root 2t, the real part, times cosine the imaginary part t, and correspondingly e to the minus 1 over square root 2t sine 1 over square root 2t. The general solution is then y equals c1 times the first solution plus c2 times the second solution. This takes a long time to write, doesn't it? Plus c3 times the third solution plus c4 times the fourth solution. There is the general solution of the fourth order equation. Finally, what do we do if we have a system of differential equations and we get complex conjugate eigenvectors and eigenvalues? What do we do with that? We recall that the general solution over complex valued functions is c1 e to the lambda t times eigenvector 1, 2i plus c2 e to the lambda 2t, 2 minus 2i, t times its eigenvector. This gives you all complex valued solutions. We proved it before. Now, how do you reduce it to the real valued solutions? You just rewrite it and pull out the subset that don't have an imaginary part. So we're going to rewrite this using Euler's formula as c1 e to the 2t times cosine 2t plus I sine 2t. Recalling that this is e to the 2t times e to the 2it, and e to the 2it is cosine 2t plus I sine 2t. Right? Similarly over here we have c2 multiplying e to the 2t for this part, and then e to the minus 2it is cosine 2t minus I sine 2t. And then that multiplies this eigenvector, 1 minus 2i. There it is, there's all, I forgot to put the vector here, 1 plus 2i, plus this. There's all complex valued functions that satisfy the differential equation. The question now is, how do we glean from there the real solutions? Right? Well, what we showed before is the real part and the imaginary part of the solution have to each be independent solutions. So we pull out the real part, or we just multiply it all out, and we see what we get. This first one with C1 multiplying it, let's pull out the e to the 2t from the whole thing. E to the 2t multiplies everything. And then C1 multiplies besides that, cosine t plus I sine 2t in the first line. And it multiplies 2i times this. So 2i times I is minus 2, so it's minus 2 sine 2t. And 2i multiplying cosine gives 2i cosine 2t. Alright, so there's that one. And then we have to add to that this part. C2 multiplies, let's see, cosine 2t minus I sine 2t. This times this, and then this times this gives us, let's see, minus 2i times minus I is minus 2 sine 2t, and minus 2i times cosine is minus 2i cosine 2t. It looks like that. Alright, now we can group the real parts and the imaginary parts. I've got e to the 2t multiplying, let's see, cosine, I have the vector cosine 2t multiplying c1 plus c2, and then I multiplies sine 2t, c1 plus c2 sine 2t, c1 minus c2, sorry, I multiplies c1 minus c2 sine 2t. And now down here, I've got a minus c1, minus 2c1 sine and minus 2c2, so I got minus 2 sine 2t multiplying c1 plus c2. And over here, in the I part, I've got c1 minus c2 again, multiplying 2 cosine t, 2t. And so I break it up like that. Now this is e to the 2t times c1 plus c2 multiplying this vector, cosine 2t minus 2 sine 2t. And I, well, c1 minus c2 multiplying the vector sine 2t to cosine 2t. Now I've got the part with I in it and the part with I not in it have to be independently solutions. So I will say that this is actually equal to, if I call this a new arbitrary constant c1 tilde, and this a new arbitrary constant c2 tilde, I observe that real solutions are obtained by letting c1 tilde and c2 tilde be real, and that will be the real subset. So I say the real solutions are e to the 2t times an arbitrary constant times the vector cosine 2t minus 2 sine 2t plus an arbitrary constant c2 tilde sine 2t 2 cosine 2t. This still gives all complex valued solutions if you let c1 tilde and c2 tilde be arbitrary complex numbers, But now you can pull out the real ones by restricting to C1, 2 tilde and C2 tilde equal to real constants.